Okay, well, we just had the infamous lox and bagels breakfast. So I understand that some people might be feeling a bit carved out, but yeah. So to combat that, we've assembled a very spicy panel here. Spicy. So let's try to keep the energy up and make sure that people aren't falling asleep. I guess we're continuing to evolve our format as the conference goes on. I think the plan for this session is that we're going to have about a 45-minute discussion that we're going to have now. Then we're going to take a little break where we're going to split into small groups as before for a few minutes. After that, maybe just hear from a couple groups before continuing on with the panel. So I guess maybe to start, if the panelists could all introduce themselves and kind of talk about some of the things that you've put up on the screen here. So go for it. Maybe Lydia, you can go first.
Hi, I'm Lydia Korre. I'm a postdoctoral fellow / at CU Boulder. I'm interested in stellar interdynamics from a more fluid dynamical perspective. So I run 3D numerical simulations, mostly in spherical geometries. I'm motivated by solar type stars and more specifically by the sun. So the setups I'm interested in are consisting of outer convective envelopes overlying stable stratified radiated regions. And then I particularly study convective dynamics in the bulk of the convective regions, so no surface convection for me. And then I'm also interested in the dynamics, balances, and transport processes within the interface between convection zones and stable layers in stars, in solar type stars. So I particularly study overshooting convection and the dynamics stemming from the interaction of these overshooting motions, both with rotation and magnetic fields. Should I say more? Or? Yeah.
Cool. Hopefully everyone can hear me okay. I have this mic sort of in my mask, but so I'm Carl Fields. I'm a postdoctoral fellow at Los Alamos National Lab. So lately I've been concerned with multidimensional simulations of stellar convection, specifically concerned with the advanced burning stages. So trying to understand what the internal structure looks like near collapse. So in the moments before iron core collapse, and how that might affect things like explodability, explosion energy, shock morphology, as well as the impact that might have on sort of multi-messenger signals. So how can we understand better the 3D convection that's going on within these stellar interiors, and what imprints we might see from those on multi-messenger signals. So that's what I've been concerned with as of lately. I'm also very interested in sort of connecting that back to 1D models, and so as well as observations outside of multi-messenger signals, sort of LIGO and neutrino emission. And so I've been thinking about a lot of these questions and sort of trying to feed off what people have been talking about in terms of observations and connecting to 1D since I've been here. So I put a few things sort of to that effect on the Jamboard.
Hello. I am Meredith Joyce. I'm the Lasker Prize Fellow at Space Telescope Science Institute. I am interested in mixing link theory, and when I say that I'm interested in that, I mean that I have it tattooed on my arm. So that is the actual formulation that I worked on in my PhD thesis. And so I am interested in basically what this parameter should be in the real world. And by the real world, I mean stellar models that need to run quickly and need to run over evolutionary timescales and need to run in large numbers for us to do things like build isochrones and model populations and model individual stars. So I would like that formalism to be as correct while being as fast as possible. And my sort of stance on that at the moment is that empirical calibrations of it are maybe the way to go, but I'm certainly interested in learning how 3D simulations can inform our prescription for NLT, especially in MESA.
Mike, do you want to go next?
Yeah, well, I guess I'm last, right? I'm the hovering head, I guess, over everyone. I'm Mike Zingale. I'm faculty at Stony Brook. I do a lot of code development, specifically interested in numerical methods for simulating reactive flows. For a long time, we developed a low Mach number or pseudo-incompressible stellar hydrodynamics code, which we've applied to for convection to progenitors of type 1a supernova in the Chandra and sub-Chandra double detonation models, to X-ray bursts, to novae, convective Urca, and electron capture supernova. So all those have been sort of convection-dominated burning environments. I'm doing a lot of work on coupling reactions in hydro in time integration methods for compressible flow now, and applying those also to late stages of stellar evolution and novae and X-ray bursts. And also I do a lot of developing of tutorials for training people on methods for hydrodynamics, and that's sort of become one of my main interests now as well.
Okay, thanks for those introductions. So I know that you've discussed amongst the four of you that you've already thought a bit about various topics associated with convection. Maybe you can describe some of this organization that we have up on the board behind you, and maybe that could be a good launching off point for our discussion.
Yes, so we were thinking maybe start with major open problems. So we have 5 sort of themes, I guess. The first, I think we decided on major open problems, right? And so we're interested to hear what folks think or believe are the major open problems in convection. And then that'll sort of guide as we move towards the different themes. We've listed 2 in blue, which I don't remember. Recent observations, I think that says, and then the sign question mark. I think is what's up there.
It's recent innovations, which was one of the questions that was posed to us, which we sort of tucked underneath here, and the sun, the tachycline dynamics, and dynamo. So those were some interest here. I'm happy. So I guess these blue sticky notes are small on your screen. I can make them a little bigger. Right. So I think we're going to look to maybe hear from some other people about what they think the major open problems were, and then sort of discuss them all as a group.
Audience, what do you think the major open problems are? Jamie Tyre. This is going to be at me. Okay.
Well, so I could try and pitch it more broadly, which is that when you look at an actual star, you get all sorts of different measurements of convection. You have some sort of photometric variability that tells you something about granulation. You have some sort of line widths in your spectroscopy that tells you about macroturbulence and microturbulence. When you do a fit to a model, you get some sort of convective mixing length that you need to fit the star. You have some sort of fits to your overshoot parameters. And so all of these things are telling you about convection. Do you have any thoughts about how you put these together to learn something physical about the convection? Or is it better to just treat them all independently and ignore it as a problem as long as you understand the convection theoretically from other things?
So I think in specific cases, and from when as pertaining to stars specifically, in particular evolutionary regimes and particular masses of stars, let's say, there are ways to inform our understanding of convection a little bit better. I don't really foresee, in my opinion, a way of dealing with the entire HR diagram in the same way. So I think our means for improvement are definitely going to be on local scales. In the HR diagram. So for example, refinements to the mixing length parameter, that doesn't really apply to anything that has, like doesn't have a surface convection zone, for example. So you're never going to really get, grand improvements for that in particular regimes. And then I think my understanding of kind of 3D modeling is that this is largely taking place in a situation where the convection is very efficient. So that's never really going to affect our surface parameter derivations. For solar models, but other people can speak to that.
Did you want to?
I think photospheric convection, for instance, is very different from bulk convection, and I don't think we have really understood these processes very well. Specifically for the sun, for instance, we don't even know whether the velocities in the interior, if the bulk vacuum interior, there's this convective conundrum, the discrepancy between observations, simulations, models, blah, blah, blah. So yeah, I think we need to understand them more independently and then try to figure out a way to connect these dots.
And Jen Van Seders, can you talk about that convective conundrum a little bit more?
Oh, maybe I'm not the expert for that, and I might call somebody from the audience to do that. Ben?
I think you could speak to it pretty well, Lydia, but I'm willing to try and speak about it. The convective conundrum in the sun is that we don't see large-scale convection in the sun, and basically any kind of non-rotating model would tell you there should be whoppingly large convective cells scrubbing the entire surface of the sun when you look at it, with very high amplitudes that would be unambiguously observable, and we don't see them. People have tried to find giant cells in the sun, convective cells that span the convection zone of the sun. They have found them and then lost them many times throughout history. And some people think that they've still found them, and like, who knows? Lisa Upton and David Hathaway think that they have found them in modern time. This is both in terms of photospheric observations, like correlation tracking on the surface, but also in terms of helioseismology, attempts to measure the amplitudes of those flows directly have either completely gone non-result. That would be like Siobhan Hanasoje and the Göttingen time distance helioseismic community, or have claimed a detection. That would be Ben Greer and the ring diagram community, but with amplitudes that don't line up with what we expect, and at a level that matters for the interior of the sun. So why aren't the global scale flows there? Why are they different than we expect them to be? That's the convective conundrum.
Hi, Vicky Antochi here. I was wondering, so maybe you can discuss a little bit about convection and rapid rotation in stars, because I can kind of visualize how convection works, right? I mean, just look at boiling water. But the moment you let the star rotate fast, how much does the convection know about the star being so fast?
Yeah, so I haven't tried to do these calibrations for rapid rotators yet, but what I can say is that the impacts of sort of modifying the adiabatic or radiative gradient directly, which is sort of what you're doing with just changing the mixing length, right? Those are very much analogous to what happens if you impede the flux with magnetic fields or anything like that. So anything that behaves in a similar way for flux impedance, which I think rotation might in some cases, could potentially manifest in the same way that changing the mixing length does. So does rotation know about this? I'm not sure what the answer to that is, but certainly there are effects that are distributed across the surface of the stellar model where, luminosity is higher in some places and lower in others. And when you're performing a calibration, that's going to affect the answer that you get.
This is Daniel Quinney. There's a recent paper earlier this year by Jeff Vassell on rotating mixing length theory. However, my expectation is that where you're really sensitive to mixing length theory is the surface layers of your star, where rotation is probably not very important. So
right, so that would be the subsurface convection zone. Yeah, is where it's most sensitive.
This is Adam Germain. I like that I see B fields up on the board because I think there's still a lot we don't understand about how subsurface convection zones interact with magnetic fields, how magnetic fields change subsurface convection zones, and vice versa. I don't really have a specific point, but I'm interested in your thoughts.
You're skipping ahead.
Okay, well, I guess I'll answer this again. What I've been working on mostly since coming here to this KITP program is looking at the surface effects on a stellar model under the influence of imposed spots, for example, which we've inherited from the YREX stellar evolution code, and a few other things where magnetism is in some way parameterized in a 1D way. And the impact of changing the spot coverage, for example, in terms of impeding the surface flux on the star is, within observed values, according to the people that do these things, similar to changing your mixing length by 20% or so, and so could even be larger than that. And my understanding looking into this recently is that when you're trying to characterize M-dwarfs and things like this, it's known that you need these very, very tiny values of the mixing length, which is maybe a little bit confusing because you're talking about stars that are perhaps fully convective or mostly convective, and that would sort of run counter to the idea that this is only happening in very inefficient regimes and very near the surface. So it is interesting that things we expect to be highly influenced by magnetic presence are also requiring these ultra low values.
Yeah, I can maybe add to that. So I guess I think about it in the context of sort of what does the magnetic field topology look like for sort of the collapsing core, and how does that translate to the remnant that's born? Because that can certainly affect sort of the explosion dynamics for core collapse supernovae. And so you might say, if you assume sort of some dipolar field morphology, then you get something where it's a much more energetic explosion than if you have just a higher L or something. And so when you get these complex magnetic structures, those are things that can sort of change your prediction about the explosion energy and potentially help you match what's observed or completely overestimate in some cases. And so those are sort of the things connecting that to the stellar model, the 3D stellar hydro simulations. These are things that sort of feed into that.
And Carl, then also the microphysics starts to become dependent on the magnetic field strength, which we don't have really good descriptions for all of that, all the transport coefficients.
Yeah.
Could you actually say a little bit more about that?
What I can say is I'm happy I don't turn on magnetic fields. And I'm not the expert on that. I'm a consumer of the microphysics stuff, but so I do flames, and conductivities depend on the magnetic field, right? And so and the orientation of the magnetic field, and so how the flame propagates through a convectively burning environment could be sensitive to magnetic field orientation and such, and that's something that hasn't been explored much.
I'm mostly interested again from a fluid dynamics perspective, where when you have interaction of convection with magnetic fields, you might get dynamo states or non-dynamo states. At what parameter regimes you get that? Also, reciprocating convection can transport magnetic fields, and this is what is believed to be happening possibly in the sun, where magnetic field is transferred from the convection down to the tachocline, where it becomes a toroidal field through the alpha omega Parker solar dynamo effect, whatever. So yeah, that's how I've been studying it.
Thanks, Lydia, for using the magic word transport in stars. We're talking about transport.
So this is a question from Pascal Gara. In her very limited understanding of the subject, she remembers that solar seismology, and more specifically the P-mode line widths, have been used to probe and or test models of convection, as the convection is both excited and dissipated modes. Has anything been done in astroseismology, and what does it tell us about convection in those cases?
Okay, I'm looking for someone this side of the room.
Like, I'll answer it, but I've answered a lot of things. Does another astroseismologist want to comment?
You're not with the rest of them.
Stratification of astroseismology.
You guys should be dispersing yourselves.
So I have no much comments for once. No, do you want?
Oops, Savita better. Actually, I think you have more answers than me. I mean, so I think the question is about the line width of the modes and the relation to the convection. I think there's more theory going on than on the observation side. People are working on trying to really understand better how the excitation of the modes are is coming from the convection, taking into account also rotation and magnetic fields, which are also impacting the excitation and hence the amplitudes and the weights of the modes. But yeah, other than that, I don't think on the observation side more things have been done.
So like, as a general picture, it's the P modes are probing the convective cavity, typically in a subsurface convection zone. How those modes are excited, that can be many things, and that's not necessarily what, well, it's not what adiabatic like models are determining, right? Because you can't get the excitation mechanism from that necessarily. But you have the kappa mechanism, the potential for convective excitation, things like that. So I mean, certainly getting the P mode spectra where the modes can be individually ID'd, that's our most rigorous test of sort of the features of the convection zone. What that says about excitation mechanisms is less clear, and I think you possibly need hydrodynamics in that case.
This is Daniel Quinney, just kind of following up on this. I think it sounds like, Meredith, you're talking about heat-driven modes, whereas I think Pascal is talking about like stochastically excited modes by, say, like a surface convection zone. Are those mode widths observable? Are those actually known, or is that set by like the 4 years of Kepler or something like that?
For solar-like stars, Rafa Garcia, yeah. For sure, we can measure the line width. I mean, we can measure the line width of every single mode that we feed. The problem is what we learn from that and how to put constraints from there to the theory. And this is what I was saying before, that I don't have much to say. Because, yeah, we have a measurement of the line width, which is the inverse of the lifetime of the mode. But then from there to the excitation, convection, etc., I will not do this right now. So.
Jen Van Saders. Another thing that the seismology can get us, but hasn't really yet, is a measurement of where the convection zone boundary is in stars that are not the sun. It comes from a glitch in the frequencies, and it's been done for what, like 20 stars? We've successfully detected the glitch, and it should be possible to do for more with longer data sets. And that actually gives you like a measurement. The models predict where the convective boundary is, right? But actually having a measurement say, yes, you've got it right, or no, you don't, could be a useful input to this kind of question.
So is that like a wish list thing, if I were to put it somewhere?
I mean, if Rafa Garcia again, if I can follow up on what Jen said, yeah, to measure the glitch, you need a broad band of modes. You have several ends because you have the helium part and the, so you have a modulation in the frequencies, and from there you can extract several components, and one of them is the base of the convective zone, etc. But you need several modes, and for that with Kepler we only have 30, 40, 50 stars in which we really can do that. You need 10 to 15 orders to really get the proper signature. And this, unfortunately, we have to wait for Plato or for TESS after 10 years, something like that, to have 4 or 5 years on data and have enough signal to ratio to have all of these N modes for a given degree to measure the glitches.
Vicky Antochi here. So what you can in principle do with astroseismology is not only to measure the light variations, but also radial velocity measurements. So if you have high resolution spectra, you can actually measure the velocity fields in different lines, which are formed different depths. So you can actually do some sort of topography of the outer layers, of the convective layers. And as far as I know, this has been done for the sun. I'm not sure to what extent it's been done for other solar-like stars, but I know that this is one of the main topics that the Stellar Astrophysics Center in Aarhus has with the SOM telescope, which is a 1-meter telescope that is observing stars like the sun to measure for long periods of time and records basically the radial velocity measurements. And this is what can be done.
I think we've moved off of major open problems at this point, it sounds, right?
Categories don't matter. Nothing is real.
Hi, Joel Ong Yale. So back to a major open problem in seismology. So for these stochastically excited modes in particular, there are two parts to the problem of excitation. The first is that we have, the center of the envelope for which modes are excited. That's UMAX. And this has been reproduced in hydrodynamic simulations. The other part of the problem, however, is the individual amplitudes of the modes themselves, and this is a major open problem. Because if you run hydrosims, you end up exciting box modes, which do not in any way correspond to the modes of the rest of the star. And the interaction between the mode amplitudes for global oscillations and the local turbulent velocity view near the surface is still a major open problem.
And any other major open problems? Okay, Rafa has one.
I just want to say that I have an open solution for once. It's an open question. So going back to what Jen was saying, so just remind that the P1 set of a Plato satellite, it's 25,000 stars with a level of quality similar to 16 sig, for those that know, meaning a little less than the sun, observed in intensity and luminosity. So it's 25,000 stars.
Cool. Yeah, that might maybe segue to the next sort of major theme, if you will, biggest issues or uncertainties, where, okay, these are the problems, what are some uncertainties therein that sort of cause or contribute to these problems, and then after that, we can start to say, okay, what are some pathways forward? So next, maybe biggest issues or uncertainties that folks have in mind. I think we've listed a few things. Magnetic fields is there again in a different way, but maybe getting to more detail at this point now about some of these challenges.
Yeah, just as an organizational thing, maybe we can spend the next few minutes discussing this, and then afterwards we'll break up into groups, and maybe in the groups you can continue to think about those issues, or maybe ways to address them, or how to connect them to other things that are going on. Yeah, so why don't the panelists kind of discuss some of these issues that they've already included to kind of start the discussion on this topic.
Well, so maybe this isn't necessarily an open problem with convection, but its knock-on effects are very severe. So the fact that we are sort of don't have an empirical basis for a mixing length formalism in 1D models, this is causing our predictions made from the models to have much larger uncertainties in them than what is actually now being reported by several space-based missions, which is something Jen brought up a few days ago. And I think there's also a general kind of lack of awareness, or maybe phobia of the mixing length parameter, because it's one of these sort of free quantities that people don't really understand deeply, and maybe it doesn't mean so much in terms of physical reality. So we're just picking a value according to the sun, and most stars are not like that, right? And it's sort of well documented in both the 3D and 1D regimes that there is probably a mass dependence of the convective efficiency. So for people who aren't aware, or maybe in the 3D regime, what the mixing length basically is it's this mean free path that sort of a diffusive parcel travels over, and this is how convection is modeled in one dimension, and sort of the how far those parcels travel is analogous to the efficiency of convection, and we basically just choose a number for this mean free path, and we do it in a arguably physically motivated way, right? So we're calibrating this to the sun, and that works very well for the sun. But in other cases, we don't necessarily have rigorous enough constraints to perform the same calibration. And so we're just adopting this efficiency parameter for the sun in every model of everything. And it's known that that is sort of a bad idea. And we're sort of starting to hone in on the fact that this has perhaps a metallicity dependence or a composition dependence. This efficiency value should probably change throughout the evolution of a star. star and not just be fixed for its entire evolution. There's probably a mass dependence, and then of course it has a huge impact on the modeled temperature and radius of a star. And so these are the things where you're getting sort of uncertainty bars of 300 Kelvin or 600 Kelvin, but observers are reporting 50 Kelvin uncertainties for things. So now that we're in this regime where observational information is so good, we need to start worrying a lot more about the mixing length, because all of our errors on reproductions are now dominated by this. So what I view as a major open issue in perhaps like all of astronomy is the fact that our error terms are dominated by this. And I don't think it's impossible to do something about it, but we can probably only do something about it, in the regimes that are of sufficiently low mass where this parameter matters. So I think that this is a problem that needs to be solved.
Yeah, I think that, so I listed, one of the things I listed was rotation, because that's something I've been thinking about in these sort of pre-supernova 3D stellar hydrodynamics models, maybe more specifically angular momentum transport. What does the model sort of tend towards when you have these 3D hydrodynamic simulations? You're able to relax them and reach some quasi-steady state. Convection, I don't know what that means. We've heard a lot of different definitions of that. For our models, when we reach some state like that and evolve, what is sort of the final angular momentum profile look like? Because that could potentially qualitatively affect sort of things like rotationally supported core collapse supernova explosions. So connecting rotation, how it interplays, as well as sort of the topology of the magnetic field. Is it amplified in the moments near collapse? These are things that, in terms of uncertainties, are present in our models and things that we're trying to address sort of iteratively and come up with the picture, or at least models that might suggest what sort of are possible answers to some of these questions.
Carl, if I could piggyback on that too.
Yep.
So I wrote 1D to 3D. Think of something else, but it also applies to rotation. If someone gives you a 1D model that they said was rotating, there's not enough information to make a 3D star from that, right? Especially, if it's not spherical, if it's rotating significantly enough. And there are methods that you solve a Helmholtz-like equation to get an equilibrium solution for a rotating self-gravitating object, but they're not really amenable to 1D models that come out of a stellar evolution code. You don't have enough free parameters to sort of give you something, and we don't even know what it would look like. And so that's one issue where if you want to model something in 3D that's based on a 1D stellar evolution code, it's not just mapping a 1D model into 3D. You have to make up some information because 3D has more, can do more things. And with convection, it's also the problem. You have a 1D velocity profile in 3D, in 1D, and if you map that into 3D, you don't have enough information to realize a 3D convective velocity field that efficiently carries away the energy that's generated from reactions. And you can have a transient and it runs away, and I'm sure you've seen that. And we all have our own different ways to do that, but you worry, have I now departed too far from what the initial model was, what the 1D was saying, if you believe the 1D? And it's a hard problem to model a 1D model that really had 3D effects. To map it into 3D is tricky.
I don't have much to add, except that I also believe that a big uncertainty is what is the effect of rotation and convection, vice versa. What drives these mean large-scale flows, the differential rotation and the meridian circulation? How are these advected, sustained, and how do they contribute to the mixing processes within convection zone and stable regions, interfaces?
Thanks, Lydia. So this is Daniel Quinney, just kind of a question related to rotation. Angular momentum conservation. We think angular momentum should be conserved. When you do a 3D model, is the angular momentum actually conserved? Why or why not?
Is it conserved? Are you asking, is it not because of numerical effects or because of physics effects?
I think physics-wise, it's conserved.
Okay.
Make it
So
numerically conserved.
numerically, there are hybrid methods that you can solve. Instead of a momentum equation, you can solve an angular momentum formulation of the equation of hydrodynamics that does a good job at conserving angular momentum. We've done it for white dwarf mergers, and it helps a lot. And it probably would help with single stars as well.
Any other thoughts, Carl?
I guess I could, for Flash, or at least the version of Flash I use, the way we kind of answer this question is by increasing the resolution and sort of comparing, just sort of characterizing how much is lost through what means and sort of how much does that contribute to the thing that we're interested in. So like for the simulations I do, it's on the order of a few percent that we lose as compared to the initial.
In how much time?
So this would
like
be
convection times, or
this would be like 10 minutes. So yeah, on the order of tens of convective turnover times. Yeah.
Jamie Tyre. So when Evan showed his movie this morning, the convection has a lot of little detailed things going on. What problems do I have to care about those details? And in what problems am I okay time averaging, spatial averaging over long terms?
Did you?
I mean, once you're simulation-wise, we're talking about, or so yeah, you need to make sure that you reach a thermal equilibrated state such that the dynamics do not change in time. So you need to look at your kinetic energy profiles and your entropy gradient profiles or whatever thermal variable you're using, and make sure that you're in a statistically stationary state. And then when you extract the output dynamics from this state, you know that they're not going to change in time. But you need to make sure that that's the case. Otherwise, you cannot extract time and horizontal averages, as you say. These are not going to be meaningful to create then models or scaling laws based on your input parameters.
I missed what the simulation was that was being referred to, but I think for what Carl and I do, we're not statistically in a steady state because we're going to blow up. So
I guess then for convection of solar type stars for sure.
Yeah, but convection in thermonuclear runaways is maybe trickier then.
But I think there's also a question about basically like numerical resolution. When you have lower resolution, you don't get those fine scale features, and how is that changing things?
Yeah, I mean, I guess one comment on that is just sort of a lot of what I do is, we run these simulations, these 3D simulations, and then at the end of the day, we'll take some angle average quantity or some, FOB average or something, and then sort of just try to look at, okay, when we go back to looking at a 1D sense, what is this new relaxed state, assuming we're in some like new quasi-steady state or something, and how's that compare to MESA? And so like even at just the qualitative sense, you might get more smoothed out sort of gradients and stuff. So those are sort of some things that might change, even if you reach some velocity value or something that agrees with MESA. And so I think just smoothing those things out, at least in the case of explosions, can certainly change things.
Daniel, I'll add, it's beyond just the resolution. I mean, my answer is always double the resolution, right? And just, but it's also your coupling of the physics. And I said this is something I've been working on quite a bit. It's very easy to do reacting hydrodynamics to first order in time. And it's a lot harder to do it to higher order because of the very different timescales between reactions and hydro and the reactions driving the convection. This is something we've been worrying about a lot. And so that matters as much as the resolution, or else you don't want to trust what you're seeing.
Yeah, Daniel Quinney, a very good point that in addition to spatial resolution, there's also temporal resolution.
Yeah.
Especially in 1D.
Well, it's not just 1D. I mean, I would say especially in 3D too. If you do,
especially in all D.
Yeah, not 3D.
Hi, Vicky and Twitchy here. I was wondering, to my knowledge, metallicity changes the convective properties quite a lot. what's the progress at the moment? How much should we worry about that, and how should we proceed, or what's the prospect for changing that?
Well, I think Anne is the expert on this particular topic, but obviously your mu gradient internally is going to change the location of the convective boundaries, which is going to change your convective properties, because where that is going to change everything. And then as far as the trends that we actually observe with running a bunch of 1D models with different mixing lengths and things like that, why this scales in a particular direction with metallicity is maybe less clear, but certainly has something to do with that. And it's sort of known that the timescales it's longer when there's higher metallicity. Is that right for the subgiant, or is it shorter? Right, yeah. Or you can say it. Okay, wait, but I didn't hear what you said. Higher mixing length at higher metallicity. Yeah, okay. Higher mixing lengths at higher metallicity. So that's right, yep. So in observations that's true, but theory is the opposite.
And how about the 3D models? What do they, I mean, the shape of the convective bubbles change as far as I know, right? So how does that affect the convection, the amount of flux that can be transported?
Yeah, I don't have much to comment on that. I guess I would just think of it as sort of a different driving energy that's sort of being injected, sort of causing the convection in terms of the 3D stellar hydro picture. Yeah, I'm not very sure on that. I know other folks have done things where they sort of have different relations in terms of the sort of luminosity they see as a function of the outward convective fluxes and stuff from different luminosities, and so, yeah.
So, for Korre, in the category biggest issues, I think in the more advanced phases of stellar evolution, the question of when and how convective shells in massive stars are interacting or merging, possibly even, is a very big issue that has lots of consequences for nuclear astrophysics and also this initial supernova state. The explodability and so on and so forth, the explosive nucleosynthesis. And once you know when, if and when and how mergers are happening, then the next question, the big issue is how to simulate that and what is the right answer when that happens, how is the energy input interacting with the hydro. And then my wish list for that would be, can we calibrate 1D TDC models against emerging or existing simulations of such convective reactive violent events?
Carl or Mike, any thoughts? Or anyone else?
I would say yes.
I second that. Yeah, I mean, just thinking of the context of sort of late stage nuclear burning these shell regions, there's a paper 8.88 or 18.88 solar mass 3D progenitor model had this sort of oxygen neon shell merger happen, and then they've actually took that model and now exploded it. Some of the things I was thinking about when I saw this was like, well, how common might this be in sort of 3D hydro simulations? And then you bring up some of the points that Falk did. I don't know. I think it's definitely possible, but I guess I'm not convinced that it's something that happens often. But certainly when it does, you should sort of understand what that looks like, what the implications of that might be for some of the things that Falk mentioned.
Any other big issues, large uncertainties? Okay, Vicky.
So we can touch it here. From the astroseismic point of view, we know that we have to take we have to combine convection and pulsations. There is an interaction, especially in order to be able to model basically where the classical instability strip begins. So that means where stochastic oscillations stop being excited by the convection, and where the couple mechanism kind of takes over. So to my knowledge, there are 3 models out there that can predict this red edge of the classical instability strip, but all of them predict it for different reasons. So the physics that are predicted to be the reason for this damping are very different. So I wonder if there will be a 4th code that can solve this issue.
Which are the ones that do well?
Well, they all reproduce this boundary, just the physical reasons are different. So it's hard to tell which one is the correct one. Some are concentrating more on the higher mass end, so basically to predict, for example, G modes in gamma Dor stars, so the Dupré group. Then we have on the solar-like star aspect, Günther Hudek and collaborators, where it's really about exciting and predicting the amplitudes of stochastic oscillations. And then we have the Chong group, where they try to, I think also more on the more massive side of pulsations. So I cannot tell which one is which, to be honest, which one is the best. If you talk to Günther, he will say that it's their code. If you talk to Marc-Antoine, it's their code. So yeah, I don't know.
Any other thoughts on that? Okay, in that case, maybe it's a good time to kind of switch things up a bit, break up into some small groups with some of people around you and discuss some of these issues, major problems, and we'll have that discussion for a few minutes, five or so minutes, and then afterwards I'll ask a couple representatives to come up and just briefly mention their discussion. Okay. Yeah. What's the question? Who wants to discuss? Any of these issues, uncertainties, open problems that we have been discussing up until now. Does that make sense?
Or you can go ahead and...
Well, so the second half of the prompts, right? So I think what we want to talk about in the groups is the potential solutions to some of these problems we've brought up, a wish list, and then the connection, the benefits to other communities from these solutions. Also, I want to talk about the LSP, the long secondary period, so if anybody wants to talk about that, you can talk about it.
For the Zoom participants, we'll set up a breakout room so you can talk amongst yourselves. Okay, everyone, let's come back to the big group. Hope you had some interesting discussions. Hope your investigations went well. So I just want to ask if maybe there's a couple of the groups want to just say a few words about their discussion. So any volunteers?
Philip Edelman. So we talked about the problem of entrainment and how, especially entrainment in dynamical phases where you have nuclear burning going on through the entrainment, which can then modify your convective boundary, and that's something that stellar evolution cores obviously struggle with, because then you get all kinds of breathing pulses like Anne showed us this morning. And that's something I think where hydrocodes might really be able to help, because also the timescales are fairly short, so it's dynamical enough for us to also simulate this and then kind of give you maybe a boundary of how much entrainment do you get? You can't have more because that's not what we see in the hydro simulation, so you can at least somehow limit it, maybe make your stellar model more well behaved. And what was the other thing?
Sorry, this is Mathieu. The other thing that we briefly discussed is what do we mean when we mean time-dependent convection? Because there are two different kinds of time-dependent convection. There is the time-dependent perturbation on a already reached steady state, for example, for pulsations in with star with a convective envelope. And then there is how do you turn on and off convection, which in some problems that I'm interested in actually matters a lot. And it's unclear to me whether you can use the same techniques in both cases.
Maybe one or two other groups give a brief summary. Yeah.
Adam Germain. So we talked a bit about how there's we need like a dictionary to better be able to translate between the 1D and the 3D language. So like with a lot of the work that Evan showed this morning, we spent a lot of time trying to figure out if there were questions that made sense in my head from the 1D language that it took months for us to figure out if they even made any sense to frame in the 3D language. And then there were outputs from that ran the other way, where it was hard to see if they made any sense in the 1D language. So, and this might be something that we can address sort of systematically by, identifying common miscommunications.
Thanks, Adam. We discussed similar things amongst.
Hard agree is what I was going to say.
Maybe one other group, or maybe also the Zoom participants, if someone wants to say something about their discussion.
I can summarize. We were wondering, is there a simple convection in a box numerical experiment that you can do to compare 1D mixing length in a 1D Cartesian box to a 3D Cartesian simulation of convection, with parameters suitably chosen that we can actually do the calculations, just to see how well they compare, so as a way to sort of validate one another.
Yeah, we talked a little bit about that up here too. I would really like to do that, and that requires establishing a common language for sure.
There was some discussion of this paper by Rayner.
The Rayner-Trompedock paper. Yeah. I mean, do you want me to go off on this now? Okay. So
the spice must flow.
Okay. All right. Here we go. So Trompedock 2014. So this is the notorious MLT HR diagram that was brought up yesterday, and it does. I read through it again last night at 1 a.m. and was trying to confirm that my delusions about this were actually true. And so the situation is that there have been a series of MLT analog calibrations using 3D simulations, right? So this is not the MLT. The mixing length does not have a meaning in 3D, but you can come up with an analog that is similar. And when you compare the 3D calibrated mixing length values to the general trends we see in 1D calibrated mixing length values, they actually do tend in the same direction, which is something I think I misstated earlier. But this is discrepant with observations in some cases. Rayner's simulations take place in the near surface convection zone. So we're talking about atmospheres and interactions with that. And this is in these domains, something like the mixing length can be reproduced and has meaning. So something that's a bit lost on me is, why is that possible in these near surface regions? Why can we get an analog of the mixing length that's meaningful, but with these deep core convection simulations or convection in a box, we can't? So what is actually the limitation there? I would need a 3D person to explain that to me, because for the 3D atmosphere simulations, this does work. And I think if we could tap into that and do it for deep core convection, then maybe we could start establishing that common language.
Jared Goldberg, I might be able to speak to that at least a little bit. So in the Trompedock stuff, the thing that can't really be done in the interior is you have some kind of t-tau relation that you can then stitch onto an entropy gradient, and then you try and match the asymptotic energy inside. You don't have you don't have the same kind of t-tau relation in the deep interior core. So what we did when we wanted in red supergiants, when we wanted to avoid talking about the surface because it's very 3D out there. And one of the things that I think could be done as an analog in the core is we basically looked at, if you have super adiabatic convection, you can get a delta entropy, and you can compare like the integral of grad 1 minus grad over grad ad up to the mixing length, and you can you can make that comparison. I haven't really seen it done for core convection, but I think that probably is the most straightforward analog.
Yeah, so another note on this is, of course, with convection in a box simulations or core convection, you don't have temperature, luminosity, and radius, right? These things to do your comparison on an HR diagram. We understand that doesn't make sense, right? But there's got to be some descriptive physics that is somewhat analogous in the 1D and 3D case. But yeah, thanks, Jared.
Hey, Meredith, Evan Anders. So I'm super not an expert on this, and I've actually never read that paper by Reiner. But my understanding is that the alpha MLT has something to do with like super adiabaticity of stuff driving the convection. And oftentimes in simulations, the super adiabaticity is like an artifact of the boundary layers, which are just simulation things, or there's stuff like that. So I think the special thing about what Reiner did is that the super adiabaticity is set by like actual radiative transfer processes, and that's easier to get right in the optically thin regions near the surface of like envelope convection stars. So that's my understanding, is that it's like you need the important physics to actually relate to the thing that alpha MLT is trying to tell you, and a lot of sims don't have that.
Right. Okay. That's helpful. And like also,
go ahead.
Sure. Mike, go for it.
Yeah, I just wanted to comment following up on that. Indeed, this goes back to that mapping problem that I talked about before a bit as well. There's a 3D paper which I won't name, that characterized convection in a stellar environment, but then they said, all right, well, let's turn off the reactions and rerun the problem, and they got essentially the same velocity field. And so, it was all driven by how their initial model was stratified, not by the reactions. So it is a tricky problem.
The other, Jerry Goldberg again, the other thing that to Evan's point that I want to point out is there are kind of two ways in which we talk about convection being inefficient, and we very often conflate the two of them. So there's one type of inefficient convection where you're near the surface, you're at optical depths lower that, optical depths low enough that radiation in radiative diffusion is starting to be able to carry some of the flux. And so that's one kind of inefficient convection, and that's what and alpha matters there.
And that's the Henry formalism in MESA. Yeah. So yeah.
Right. That's the Henry. Yeah, that's the Henry formalism in MESA, and also that's basically the regime where the Trampedach stuff is taking place. You can also have inefficient convection in a very optically thick region, in the sense that the gradient is just super adiabatic. And so the entropy gradient is negative. You have fluid elements being accelerated, and then as they grow, they actually sort of take in heat in some MLT picture. And that's we call both of those inefficient, but they're two actually pretty different regimes, and alpha matters in different ways in both of them. And other mixing length parameters matter more. So like in the Henry formalism, everything that isn't alpha doesn't matter in this super adiabatic type of inefficient convection, but the Y parameter and all of the other mixing length theories parameters matter a lot in the radiatively inefficient convection.
Cool, thank you. Radek has.
Just a comment to this work by Trampedach Radek Smalls here. Sorry. In fact, this was applied to one-dimensional evolutionary code by Salaris and Cassisi. So they did change the mixing alpha MLT and the tau relation as the star was evolving. So they were then comparing the results with a standard evolutionary model calculated assuming solar calibrated alpha MLT and standard t-tau relation. And surprisingly, the effects are not large. So the shift on the RGB is below 100 degrees. In this parameter range considered in the simulation by Trampedach.
Yes, that was my understanding as well, is it actually doesn't have as large an effect as you might think for a lot of this stuff, which is, okay, I'll say that. Yep.
Hi, Vikantochi here. I think I'll try to repeat my question from yesterday or my wish. Can we have this kind of HR diagram also for a high mass, for the high mass stars? Intermediate mass stars to like OBAF?
No, because okay, so MLT HR diagram in the Trompedox sense, but also in the externally calibrated mixing length sense. This is reliant first and foremost on the existence of a subsurface convection zone that is thick enough to exist. But then the thinner that zone is, the more the mixing length matters, which is why you get into kind of a disaster regime with like A and F stars and things like this. So this is where you're going to get a huge degree of sensitivity to your mixing length choice in a convection zone that might even, disappear if you're not propagating your model correctly in your evolution. So that gets very, very tricky. It's hard to do those things. And then, when you have a radiation zone just right below the atmosphere, this is not a meaningful thing to do because the effects of changing the mixing length in the core don't manifest in terms of surface observables at all. So you're not really getting variations in luminosity, temperature, all of those things. The things we need to actually match in reproductions to real stars are not changing when you're modifying the mixing length in other regimes besides the subsurface convection zone. So anything beyond that or anything in that regime is not going to permit a 1D calibration in the sense that I have done them. Jared perhaps knows more about what to do with very high mass stars, but I think there's at least a gap somewhere in the HR diagram and in the mass spectrum where it is not going to be possible to do this because it's not meaningful to do this.
Daniel Quinney, I just want to add something about thinking about core convection, at least, or cases where you have very efficient convection. At least my understanding of MLT is that it's a way to predict the superadiabatic gradient. And if you run a simulation of inefficient convection, then you can measure the superadiabatic gradient. When I run a simulation of efficient convection, actually part of the convection zone is stably stratified. So if I calculate the entropy gradient, sometimes it's positive, sometimes it's negative. I don't trust the value of what I calculate there. So because of that, I'd be very uncomfortable in trying to relate that to anything associated with mixing length theory. Maybe some of the other people who are doing simulations of a more efficient convection could add to that if you have anything.
I don't know, I also see subadiabatic layers sometimes, depending on the input parameters, especially in inelastic cases or when you have stripped buoyancy frequency profiles between convection zone and radiative zone, so I don't know.
Yeah, not much to add to that. Once you get to advanced stages and stellar interiors, the things just are kind of, we kind of just take them, the MESA model and sort of characterize sort of the regions, but often it is very hard to sort of compare back to and say, okay, we see a widening of the convective region here, so yeah, it is a challenge for us in our simulations.
Jen Van Seters, can somebody give me an example of a place where there's efficient convection that you care about what the mixing length is? Like, if it's very efficient, right, it's just adiabatic stratification, so you shouldn't actually, you can pick almost any mixing length you want and get the same structure. So it's really only, I'm just checking that I understand, right? It's really only the super adiabatic places where it matters. So if we're in a regime where there's
Yeah, it matters more the less efficient.
I was just gonna say, if we're in a regime, and I don't know this, are most convective cores in a regime where they are super efficient convection? If that's the case, then we don't actually need to worry about MLT in them, right?
I think this is exactly right, what you're saying. In most cases, it's efficient. Falk Herwig. I think we're even in the deep interior where convection is mostly exactly adiabatic or almost exactly adiabatic. My feeling is that when we're getting to the point where we're really trying to create a careful model for the convective boundary mixing, we will have to tie whatever happens in the boundary to the conditions at or near some anchor point. That anchor point is probably going to be Schwarzschild, but something is going to happen right inside that boundary, and that will depend on alpha MLT.
The other thing I'll say, and maybe this is just a bone I have to pick with the concept.
Name.
Jerry Goldberg again. Maybe this is just a bone I have to pick with the concept of a mixing like theory convective velocity. But if you care about the convective velocity, then alpha matters because those two parameters are directly related. And so if you want to say something about the characteristic velocity of transport, and I say transport, it could be heat, it could be energy, these could be separate values, I don't know. But if you care about those velocities, and that also probably relates to, you know, how much penetration you get, then it actually does matter what your alpha is, even if you can't actually calibrate it or you don't care about it for the fact that it, you know, it is adiabatic, etc. So that's really where it does start to matter, even if it's not necessarily a meaningful concept.
It also matters in the Falk-Herwig, it also matters in the deep interior when you have these convective reactive flows, because where the energy will be deposited that is additionally generated from bringing in fresh fuel into the convection zone depends on the convective speed, and it will be deposited where the convective speed is equal, or timescale is equal to the reaction timescale, and that can make huge differences.
Mike, I heard someone say reaction.
You did, yeah. I know. I agree with Falk, especially with things like, you know, mixing CNO in for hydrogen burning.
Carl, any thoughts as well? Expert on reactive flows.
Yeah, not in particular. Basically, just echoing their thoughts. You know, something I've been concerned with is sort of just comparing what are the convective velocity speeds that we find in our different simulations for a given oxygen shell, and is there something we can take sort of from these 3D sims and sort of make arguments about. And so that's what I'm pretty concerned with, and making sure we get that right in our simulations, because it can make an impact. You know, in the case where you get extreme sort of entrainment of shells on top of the oxygen shell, like, you know, the carbon, there's a paper a few years out looking at this. You can increase sort of these odd Z elements and sort of the nucleosynthesis production and stuff. So like they have they have consequences sort of if you don't treat these things properly, in these shell regions. So.
Okay.
Anne?
Yeah.
Okay, so I think that one place where, Antul, I think that one place where all this discussion might be very useful to think about is what I talk about the breathing process on the cohelium burning phase, where obviously something is wrong, we're doing things wrong, and it's probably going to be, it's a huge convective core. You bring in a little bit of helium from the absorbed shell above, and you cannot imagine that this is just going to go to the center, burn immediately, and that's what happens with the classical MLT. So I have a lot of hope that you are going to figure this out with those 3D simulations where you take into account the real velocity fields.
Ben Brown, thinking about a case where the velocities of transport are very different. Jared's kind of point and question. One neat example of this that comes from just simple compressible boxes of convection. Stratified convection is asymmetric. The upflows are slow and broad, the downflows are fast and narrow. Doesn't matter at all for the heat transport because the downflows largely cancel themselves out. They transport enthalpy, but they also transport kinetic energy. So they kind of wipe themselves out of the average. And so the velocity that you infer is some kind of like small scale, like average thing. You put a magnetic field in that thing, the only thing magnetic fields feel is velocity. So they actually get stuffed downwards to the bottom of the box by the asymmetric downward flows, preferentially. They ignore the upflows. So if you care about something like vector transport in your system, that might be extremely different than heat transport. So an MLT velocity from heat transport that does a great job of matching a structure might be completely the wrong thing to plug into some putative dynamo model as the representative velocity scale for your alpha effect or whatever else. It's probably something completely different.
So topic switch, but I want to launch back to something something Carl said about, the convection impacts the nucleosynthesis. We've also talked a little bit about how the convective assumptions affect the location on the HR diagram. Are there other diagnostics that you think are up and coming that are going to really give us constraints on how we should be treating convection?
So I guess one of the things that I think about are sort of the convective structures of the star for collapse. And I brought this up a bit earlier, but so when you explode a star in 3D, starting from a 3D initial model where you have some information about some velocity field, you'll get, so what'll happen is when you compute the gravitational wave strain that's produced after bounce and explosion, the explosion phase, as you accrete these different burning shell regions, depending on the scale of the value of the Mach number, these regions, you can have a large sort of broadband emission of gravitational waves across a range of frequencies for more perturbed models. And so that's something where you're actually imprinting on top of this, so if you're familiar, sort of this this frequency uprise as the proto-neutron star cools, this is overlaid on top of that from these shell regions. And so if this is something that we see, or at least we want to sort of create sort of the next generation of gravitational wave template models, it's very likely that these shells are convective when they collapse, and then they might show up. And so that's one example of something in terms of advanced LIGO and sort of observables, if you will.
Hey, Carl?
Yep.
Can it affect the outgoing neutrino spectrum as well, or no?
Yes. Yeah, I can. In different ways, it's not as pronounced, but it certainly has an impact there as well. So tying to that, and you see dips in the neutrino luminosity, so, but it's very, very prominent in sort of the gravitational wave spectra that you produce, even for non-rotating models, because all stars will have some sort of convection that is accreted, so the relative scale of that could be important. Any other comments?
Okay, we're starting to run out of time. I want to reserve the last 5 minutes for the panelists to maybe give, each one give like a 1 minute takeaway points from the discussion. But maybe with the few minutes that we have left beyond that, might be good to think about kind of how are we going to start to tackle these issues that we've been discussing. Any thoughts?
More MLT calibrations forever for the regime where it matters, and maybe some clarity in a paper about like where this does matter, right? And I don't know if a really good sort of summary of the synergy between 1D and 3D differences has been written, and that would be really useful. And I'll get to that in 2026 maybe.
So Daniel Quinney, there have been several mentions both today and also earlier in the conference about kind of having a dictionary between 1D and 3D. This is part of the point of this conference, of this program, to get people to try to speak in the same language so that we can figure out these things. I personally, as a 3D modeler, I don't really know how to get an alpha from a simulation. It seems like some people know. I don't know if many of the 1D modelers know, but this is the type of thing that I think would be really useful to try to sort out, not just for alpha MLT, but for other issues.
Yeah, we had a few other things listed for that, I guess. Observations, exascale architectures, so sort of this, I could use this from next generation, but that's, what gets funded, I guess. So like sort of supporting multi-scale, multi-physics, 3D stellar hydro simulations, So advancing that forward, folks are working on that. Mike's a big part of that. But that's sort of complementary to sort of making sure we're making progress on speaking the same language. So, yeah.
Related to that, I added something. There's a lot of tools, software tools available, Mesa, the codes that Carl and I work on and so forth, that the community can download and run and show something results from. But the codes are getting increasingly complex, and I think it's important that we remember that if we want these codes to continue to evolve, we need to train the next generation of people not just how to use the codes, but actually how they work, how the guts actually work, so that they can develop the next generation of tools. And instead of relying on just some small group of people to be the tool writers. And so I personally think that's an important thing. It's something that I work towards.
Vikander here. So I think what we have not really discussed a lot and would be very important, so not only to have a dictionary between 3D and 1D modelers, but also 3D, 1D, and observers.
Oh, yeah.
I think it would be very important for us observers to understand what do you need, what can we observe, and so how can we compare the results coming from the 1D, 3D, and observations? Because otherwise you will never know whether your models are correct, and we will never know what prescriptions to use to fit our observations.
There's comfort in not knowing, though, right?
I wanted to spring off of what Mike said. Maybe this isn't Adrian Fraser. I wanted to spring off of what Mike said, and maybe this isn't really news to anyone, but I mean, as a postdoc, I look at I care about job security, and I care about how like Daedalus works. I really like looking into the guts of other codes, and I don't think that's going to get me a permanent position. If I'm being honest, I see who's getting jobs, and it ain't people doing that. So like, I totally support what Mike said, but that's just not what the system's set up to do. Is that too pessimistic?
No, I think you're right, Adrian. But I think that's a problem.
Okay, we have time for one quick comment, and then I'm going to switch to the panelists. Just 1 minute takeaways from each one. But first, we have
Evan Anders. I just wanted to say, as far as the observations go, what we need as modelers is like clear consensus on things that you agree are robust observations. I think it's hard for us to understand, like, there's a lot of observation papers, and like which ones do pretty much everybody in the community agree are like good, and which ones are like questionable, and the same kind of goes for simulations, right? So probably just here's a small list of really robust observations that we can't explain, is what I would like, because I can't tell which things are like definitely need explanations or might actually not be real.
Thanks for that last comment. So let's turn back to the panelists. How about Mike? How about we start with you? 1 minute closing remarks.
I think I'm more confused now about what convection is than before. But I don't think that's a bad thing. I think I didn't appreciate until I started talking with my fellow panelists just all the different ways that we use convection, that we talk about convection, and how we all have, if you ask someone what convection is, we all have our own default answer to it, and very few of us overlap in that, and so I think that was quite interesting. So I think that's my main takeaway, is there really is a wide variety of ways people think about convection, and with Daniel, when you write this dictionary, that'll be great.
Great, thanks, Mike. How about we start with Lydia and go down the line?
I guess I had the exact same point. I really think I know less now than before.
That's our goal.
Okay.
Lars, don't listen, Lars.
You succeeded. So yeah, I really would like to be able to translate my 3D results to other communities and vice versa. And also, what else? Rotation magnetism is something that needs to be studied more systematically, at least from a 3D numerical simulation perspective. Yeah, more or less that.
Yeah, so I'm sort of echoing the same sort of thoughts. I'm very much more confused now, which is great because a lot of folks in this room and on the call brought up a lot of questions that are part of things that I've not thought about. Sort of, one particular is what Jared talked about, sort of this different idea of inefficient, or sort of how we make these different definitions within the languages that we speak. And how we need to be sort of more mindful of that. So that's definitely something. When I say this is a velocity, I get, what do I mean by that in my simulation, and how is that relatable? Questions that I'm going to think more rigorously about and asking myself, and sort of bridging to 1D modelers and observations, of course. So, yeah.
I am excited about all of the things that I don't know, which is a lot of things. It was a lot of things when I came here, and it's more things now, and that's good. That's a good trend to have. And so, yeah, I mean, I was like surprised at how difficult it was, relatively speaking, for the four of us to have a conversation yesterday, right? Like, we're in such different domains that we had to have a little bit of a, what do you mean when you're saying this, kind of, pre-explanation procedure before we could even talk. So I think that there's a lot of talking about how we should make a common language, and I think we should now do it. I think we should do that. And then I think ideas can come more easily from there.
Great, thanks. And how about we thank our panelists?